Jumbo. Hello. My name is Michael O'Toole, a science coordinator at St. Vrain Valley Schools and leader of the Kilimanjaro Student Learning Expedition. Now before we start, remember, you can join today's conversation on Twitter with the hashtag #DiscoverKili. That's Discover, K-I-L-I. Send us your questions and hopefully we'll be able to answer a few. We're coming live to you today from Westview Middle School in Colorado, the foothills of the Rocky Mountains. If you've ever visited Colorado, the Rocky Mountains, you know it's a pretty special place. Living here, I always want to know a little bit more about what it's like where I live. And in fact, just last week, a team of students, teachers, and scientists from around the world wanted to do the same thing. We traveled to East Africa, to a mountain that would tower a full mile above the highest peak here in Colorado to understand what geographers call a sense of place. Now, a sense of place is a pretty simple thing to understand. Where is this place? What's it like there? And what kind of things happen there? Today, we're going to take a look at Mount Kilimanjaro, the tallest mountain in all of Africa. And I hope you and your classrooms out there can take a look at this trip and identify some similarities and differences between where you live and the mountain. And if you can do that, you'll be well on your way to understanding and being able to describe where you live, your sense of place. I'm so excited to be your tour guide today, but like any expedition, we need a strong team, and this time we have it. We're paired up with St. Vrain Valley Schools, the Education Foundation for St. Vrain Valley, Discovery Education, the Globe Program, Globe Africa, and Globe Oman. And let me tell you a little about Globe Oman. Just amazing. These students and teachers, 14 of them, from the Arabian Peninsula, went to a place that's so drastically different than where they live. Two things it rarely does in Oman is rain and snow. And these guys were fearless in going to a place to understand a little bit more about where they live, and that was quite remarkable. So Adira, Ahmed, Anas, you guys are incredible. One of the things that we wanted to do today is take a look at without this program, we are actually thankful for all of these groups, and we're excited that all of them are here. We couldn't really have done this without the strength and collectiveness of all of them. Here to talk a little bit about the Globe program is Tony Murphy.
Hi, my name is Tony Murphy. I'm the director of the Globe Implementation Office, and I'd like to tell you a little bit about the Globe program and what it actually does. So the Globe program is a citizen science student-based project that gets teachers and students together to collect data that scientists can then use in their research. And one of the campaigns that we're working on right now is the Soil Moisture Active Passive campaign with NASA, where students are out collecting soil moisture data and then sending that into our database, the Globe database, and the scientists can then access that. As part of the campaign and as part of a recent Kilimanjaro learning expedition that we had in Tanzania, we had students collect some soil moisture data, and this will be used by the scientists to actually look at soil moisture in Tanzania, but also looking at it as part of a global campaign. So the Globe program is an exciting way to get students involved in hands-on science and getting their teachers to connect with scientists to work on specific projects. We really focus on collection of data and actual entrance of data into the database so that students can perform research on that data and using that data wherever they are in the world. We welcome you to become part of the program, and as part of the Kilimanjaro Learning Expedition, I'd like to thank all of the different people who are involved in that. The St. Vrain School District Foundation, the Globe Africa, Globe program itself, and then also Discovery Education, who's hosting the webinar today. So thank you and enjoy the rest of the webinar.
Thanks, Tony. In fact, the exploration of Kilimanjaro started out as a Globe Africa product about 7 years ago. The Globe program works to develop students to become citizen scientists, to use standard protocols to collect data and enter that data into the Globe database. That data is important. It's used by fellow students around the world, as well as scientists, researchers, and policymakers to make informed decisions. Over the last several years, we've been collecting data, and we're very proud of that data fact. Now, we see some questions rolling in, and one of the questions is, why Kilimanjaro? And that's a pretty important question, and it's one that I'm really excited to share with you today. Kilimanjaro is a magical place. It's a mountain that sits near the equator, surrounded by the plains that we call the Serengeti. Right there stands a mountain with snows and glaciers on top. It's quite remarkable. Climbing Kilimanjaro is like walking from the equator to the North Pole in just a series of days. Every single biome that you could possibly experience is there along your journey. Kilimanjaro is also the largest freestanding mountain on Earth and one of the largest volcanoes. This year, we were lucky to have a teacher from right here in Westview Middle School with us, Jamie Snyder. Jamie's actually a former volcanologist, and it was great to have her along with the trip. So, Jamie, welcome, and thank you for taking time away from your students today.
Thanks for having me, Mike.
Man, former volcanologist. That's got to be pretty cool to have on a business card.
Yeah, it was a lot of great past experiences I've had.
Excellent, excellent. Can you tell us a little bit about the geology of Kilimanjaro?
I would love to. Kilimanjaro is an amazing geology. In fact, it's a dormant stratovolcano that's formed in the East African Rift Valley. Now, it's a divergent plate boundary that allows magma to get close to the surface. Kilimanjaro is actually 3 volcanoes, Shira being the oldest, Menwazi, and then Kibo is the youngest. However, it's not been active in modern times, but there are still active fumaroles. Lava bombs from Kibo's past eruptions, dating to about 200,000 to 400,000 years ago, are still visible across the whole Shira Plateau on the western slopes. We were lucky that that's the route we took, and we got to hike right through all these lava bombs. Then our trek continued, and we started to climb over various different lava flows of different mineral contents. We then hiked through U-shaped valleys that are covered in glacial moraine. The region is still tectonically active, and faulting is clearly visible within the lava flows. There's a lot of water that aids in the process of weathering and erosion. With Menwazi in the background, you can now see that we've been hiking over volcanic scree that is present from over 16,000 feet and higher. Kibo is a well-defined crater with an ash pit. We actually camped right in that crater and then climbed up the steep walls to the summit. And our tents are right in the middle of that picture that you're looking at right now. About 80% of the glaciers on Kilimanjaro have disappeared, but some are still present around the summit. With the melting of these glaciers and the active tectonics, Kilimanjaro is a dynamic and ever-changing volcano.
Thanks, Jamie. Now,
Yes,
it's one
thank
thing to talk about the mountain, but let's take our visitors on a virtual tour, what they would expect if they were to hike along with us as we move up.
Sounds great. Here we go.
So there are 6 distinct biomes on the mountain. Let's take a closer look at each as we climb together. Starting with cultivated areas. The elevation here is roughly 2,500 to 6,000 feet. Kilimanjaro's rich volcanic soils are irrigated by water from rainforest higher up. These areas have attracted farmers to settle the mountain's lower slopes. Today, what used to be natural brush and lowland forest has been replaced by crops and grasslands. Crops such as potatoes, coffee, and carrots are pretty common. The mountain's a jewel for Tanzania in that it creates its own weather and rain, and the Chaga people who live in the foothills take every advantage of that. Now, moving up to the rainforest, the elevation is roughly 6,000 to 9,200 feet. Accumulating close to 6 feet of rain a year, the rainforest is dripping, humid, and bustling with life. The temperatures generally range between 70 and 80 degrees Fahrenheit throughout the year. Now, this is my favorite zone on the mountain because we walk through it and we hear many more animals than what we see. Songbirds, colobus monkeys are there to greet visitors who start to climb Kilimanjaro. There are many different tree species as well. And near the top of the forest is a layer of clouds, which blankets the forest throughout the day, and these clouds are an important source of water for the areas below. Moving further up, we enter the heath zone. The elevation is roughly 9,200 to 11,000 feet. Above the rainforest, lower rainfalls result in much sparser vegetation. The lower elevations of this region are characterized by a wide, rolling meadow of giant heath plants and many small wildflowers. Heavy mist often cover the area. The heath zone may get 30 to 40 inches of rain, and many grasses there are abundant and vital for safeguarding the soil. One of the cool parts of this biome is the transition between the tall canopies of the rainforest and the heath zone itself. It's as if someone drew a line or a boundary right there on the mountain. Moving further on up, we reach the moorland, 11,000 to 13,200 feet. At higher elevations, the mountain is much drier, getting only 20 inches of rain per year. There's also greater fluctuation in temperature, with high temperatures from 80 to 90 degrees during the day and freezing temperatures at night. This region has several distinct plants, including the giant lobelia and the senseo trees, which can only be found on Kilimanjaro. These plants have been very resilient to survive these conditions. To tell us a little bit more about the lobelia, here's our head guide, Julius Minja.
It's an endemic plant on this mountain. It's not found anywhere else. And you see it is very, at night it closes, and then during the day it opens. So you can see it opens and so that it can keep water inside. And during the day it can allow sun to get in so that it can manufacture its own food. Yeah. And it grows above 3,500 meters. This plant is very unique because it doesn't grow below 3,500 meters.
Does it need a lot of water?
Yeah, and also it can, manage to survive in this tough weather condition, especially cold and ice.
Thanks, Julius. We would have loved to have him here live, but he's actually back on the mountain already. Now, one thing before we continue our climb, I do want to give a shout out to the guides and porters of Kilimanjaro. They're the real heroes of the mountain. Without them, we would have never made it. The porters carry our gear, the guides are so knowledgeable, and they love sharing their mountain and the passion for their country with their visitors. So thank you, Julius, the team. We had about 22 people on the mountain, but with all of our guides and porters, we had over 100. So it was a small village making their way up. So let's continue on. Next, the Alpine Desert. The Alpine Desert is roughly 13,200 feet to 16,500 feet. This is a harsh, dry, windy region consisting mostly of bare rock and ice. The temperature of this area ranges from below freezing at night to over 100 degrees during the day. The air is very thin and the radiation from the sun is intense. It rains less than 10 inches per year and there are very few plants, mostly lichens and small mosses. Our team described it this year as if we were walking on Mars. Very, very cool. Next, to our final destination, the summit. The elevation is roughly 16,500 to 19,340 feet. The summit is an Arctic zone characterized by freezing cold nights and burning sun during the day. At the top, the oxygen level is roughly half of what can be found at sea level. The thin atmosphere offers little protection against the fierce rays of the sun. No matter what anybody tells you, it's hard to breathe here. You can take a couple steps and then you need to rest and catch your breath. This region receives less than 4 inches of precipitation per year, usually in the form of snow. The massive glaciers that Jamie spoke of earlier cover about 1/3 of the mountaintop and the remnants of what was an ice cap that covered the entire mountain only 1,000 years ago. However, the glaciers are disappearing at such a rapid rate that there's concern that the ice may not be there, may disappear completely in 20 years. Now, wow. Just a couple minutes, we climbed the entire mountain. That's amazing. We stayed warm, no altitude problems.
No altitude sickness, no sleep deprivation. That was much nicer.
That was great. Now, Jamie, not only did we climb, there was a lot of science on the mountain. Can you share a little bit about the science that took place?
Oh, yeah. It's one thing to climb a mountain, but it's one thing to use Kilimanjaro as basically a walking classroom. And that's just what we did this year. We followed a GLOBE protocol, and we collected data for hydrology, for atmospheric, for land cover, and for soil moisture. And we then used the new GLOBE mobile app to then enter all this data into the GLOBE database, as you see here in the pictures.
One of the things that we're very proud of is how many students and teachers from all over the world follow us. This year was no different. We had over 57 countries contribute questions, data, and share their biomes.
57, that's really great.
Yeah, it was quite remarkable, and we're pretty excited about that. I just wanted to give a shout out to a couple schools that have been with us from the start, and we wanted to say thank you. First of all, Nottingham Elementary School in Houston, Texas, the Notre Dame School in the Dominican Republic, Cole Middle School in Rhode Island, Ruth Hill Elementary in Lincoln, Nebraska, St. Xavier High School, Louisville, Kentucky, Talbert Middle School in Fountain Valley, California, James Monroe Elementary in Everett, Washington, Burlington and Legacy Elementary Schools, as well as Trail Ridge Middle School right here in St. Vrain. Now, these schools follow along, but Jamie, I'm kind of curious, how did your students follow your trek?
Well, of course, I have to give a big shout out to Westview Middle School. Thank you for all, and I know you guys are watching right now and supporting us right down the hall, so thank you. And our students have been working really hard to be thinking like a scientist, learning how to make observations. So before the trek in Tanzania even began, my students were up right in our backyard at Rocky Mountain National Park, and they were taking water samples following the GLOBE protocol. We were testing for conductivity, for pH, temperature, and even dissolved oxygen. We also learned about the National Park Service and the mission, because Kilimanjaro itself is within a national park as well. In addition to that, we wanted the students to learn about donating to countries that are not as fortunate as the United States. As you can see, our students signed soccer balls, and then when we gave that to Tanzanian students, they were extremely excited. We then used a platform called iSeen to then collect our data and be able to collaborate with countries around the world. So my students are currently talking to students in the Dominican Republic, as well as to the Omani students who followed the GLOBE protocol in Tanzania. We also held a webinar for the students from Colorado to talk to the students, and these Omani students were in Tanzania talking live to my students here in Colorado. They were able to ask questions about science, but also cultural questions as well. As a teacher, it's my goal for students to see the larger picture and to be able to learn and relate it globally. I love when learning extends beyond the brick walls of this building and the invisible city walls, and they see that larger picture. This global experience would not have been made possible without a grant from the Education Foundation for the St. Vrain Valley. So thank you to all for making this a very positive and achievable experience for our future generations.
Wow, it makes me want to go back to middle school. There's some pretty exciting things happening here at St. Vrain.
Some of my students might say yes, and some might say, oh, it's a little difficult.
Yeah. Well, great. And there's another group that was following along, and that's the scientists and researchers from NASA.
NASA, yes.
NASA. In fact, the SMAP satellite mission and their team was following along. Here, take a look.
Our future is all about water. It's too wet where you want it dry, too dry where you want it wet, and you need water for plants to grow. SMAP will help address this issue by tracking water around our globe.
SMAP is an acronym for Soil Moisture Active Passive. It's a satellite that studies the Earth's moisture content, where it is, where it comes from, where it goes.
Soil moisture plays a very active and vital role in the water cycle, and we all depend on it in ways that we don't realize every day.
Every 3 days, we'll have a soil moisture map of the entire Earth, and it will allow scientists to track water availability around the globe, which will also help in guiding policy decisions. The measurements are really important. In terms of our future, one of the biggest issues is water, and SMAP will help us better understand this mobility of water from one place to another. I think it has the potential to touch everyone's life.
As we discussed earlier, this exploration of Kilimanjaro provided us with numerous opportunities to conduct science research. We're pleased to welcome Dr. Erica Potus from the Jet Propulsion Laboratory in California here with the SMAP satellite mission. And Erica, thank you for joining us. We're pretty excited. You were supposed to be on the mountain. It just didn't work out. We're glad you're here today.
Thank you. It's great to be here, and it's been very exciting for me to follow your trek up the mountain, even virtually.
Oh, it was great. And can you tell us a little bit about SMAP?
Sure. So SMAP is a NASA satellite, and we launched on January 31st, 2015. And the objective is to measure soil moisture globally. So that's the amount of water in the soil. And why is this important? Turns out that soil moisture is a very important environmental variable that changes very quickly, and we don't have a good way to measure it globally until now with SMAP.
Excellent. So tell us a little bit more about the satellite. What does the active-passive part in the title mean?
Yeah, great question. So active-passive is descriptive of the type of instruments that we have in order to make the soil moisture measurements. So active describes the radar instrument that we use. And the radar is similar to a camera with a flash. So we emit a radio signal to the surface of the Earth, and we measure the portion of that signal that scatters back to the satellite. And that signal contains information about soil moisture. The radiometer is similar to a thermal camera, so we measure the energy that's being emitted from the Earth as a thermal camera would, except we're measuring the energy in a different frequency range. And the radiometer is passive because we're just listening to the emissions. We're just capturing these emissions.
Excellent. I'm sitting here taking notes. This is great. What's the advantage of using radio waves?
So there's a couple of great advantages in using radio waves. One is they're very sensitive to soil moisture, but also we can observe the surface of the Earth regardless of almost any kind of weather condition, and we can see the surface of the Earth regardless of their night conditions.
All right. You've mentioned inside the satellite a couple times. We have a question from one of our friends in Oman who asked, what's the large circular disk on top of the satellite?
Yeah, that's another great question. So that large circular disk is our antenna, and that allows us to observe the surface of the Earth. And that's really the great engineering achievement on SMAP. It's this super large antenna. It's 6 meters in diameter. That's about 20 feet. And it weighs very little, so about 120 pounds. And as you can see on this video, that antenna was folded on the spacecraft, and once we were up in space, it deployed like a camp chair.
All right. We have a question from South Africa now. It talks about how do you actually measure soil moisture, and is it useful?
Sure. So both instruments are sensitive to soil moisture, and it's useful in many different ways. If you think about the amount of water in the soil, that water has the potential to evaporate. And when it does, it plays a huge role in cloud formation and in weather. So knowing the amount of water in the soil can help us better predict weather. Also things like floods. So soils are like sponges. They can only hold a certain amount of water. And if you know that your soils are near saturation, for example, and that there's a big rainstorm coming, then we can predict that that area is at risk for flooding.
Excellent. One of our followers, in fact, my former science teacher, Marty O'Toole from Louisville, Kentucky, had a question about the radar itself. It's his understanding the radar is not functioning anymore. Is this true?
Yes, so that's correct. The radar ceased to function in early July, but we collected 2.5 months of global radar data, and we're in the process of deriving some very useful and important products from this radar data, products related to characterizing land cover and identifying wetland ecosystems. The SMAP mission science continues with the radiometer, and we're producing global soil moisture maps with the radiometer data. So what you're seeing on your screen is a map that was produced with data acquired over 3 days in April. And the yellow areas are areas that are very, very dry, and the blue areas are areas that are very, very wet. And then the greens are intermediate values. So the radiometer is working beautifully, and this type of data allows us to see soil moisture and how it's changing on a daily basis, on a seasonal basis, on a yearly basis. And this type of information really helps us understand what are the impacts of climate change and how different areas of the world are being affected.
Well, excellent. Well, the good news is the mission's still ongoing.
Absolutely, yes.
Excellent. Now, it's one thing to go outside and collect soil samples, but why from space?
Yeah, so space gives us that really unique perspective of being able to observe remote areas on a continuous basis. So it would be impossible to send people out with a sensor and measure soil moisture over very large areas on a continuous basis. So really the only way to do it is from that space-based perspective.
Now, on the flip side, one of our goals of our research project was to collect soil samples from each biome on the mountain. So as we trekked up, we took a soil sample from each. Now, understand from space, but is this data still important? Would you want this?
Absolutely. It's actually really important because the data that you collected and the data that students collect around their schools is valuable to us so that we can compare that to the satellite measurements, and we can have confidence that the satellite is making good measurements of soil moisture. So this data is critical for quality assessment of the satellite data. And NASA has a free data policy, by the way. So all of this map data that's collected and all of these soil moisture products that are being generated are being made available online.
Wow. I tell you what, one thing all of our future scientists out there might not know is they could actually take part in your mission through a partnership between NASA and the GLOBE program. Can you tell us a little bit more about that program?
Yes, so we're extremely excited about this partnership because it allows students real hands-on science and understand about soil moisture, the importance of soil moisture, and be part of our NASA mission, our NASA SMAP mission. So as I said, these data are extremely valuable for us to be able to compare it with the satellite. And we encourage you, and we hope to get more data, because that's really what's important, is this data series of data, of measurements that you collect, so that we can see how things are changing.
Excellent. So any students and teachers out there wanting to learn more, you can go to globe.gov. Whether you're a GLOBE certified teacher or somebody new wanting to learn more about GLOBE or how to get involved, all the information should be right there. Now, it seems like our time's already up. It's amazing we just started. But well, thank you very much, Erica. Thanks to Jamie, all the members of the GLOBE team on the mountain, Jesse, Jason, the Omani students, teachers, as well as the staff and students here at Westview Middle School. A special thanks to Discovery Education, who helped us put this production together. And thank you to all of the students out there that sent Biomes questions and to follow it along. It was as if you were there on the mountain with us. We summited, there might have been just a handful of us there, but all of you were with us, and it was quite remarkable. An archive of this event actually will be available online at discoveryeducation.com/Kilimanjaro. So another Swahili phrase, asante sana, which is thank you very much, and so long.
Adios.